Welcome to this explainer. Yo, today we're going to take a pretty fascinating journey together. We're tracking the evolution of artificial intelligence, starting from the incredibly frustrating limits of its early days, right up to the literal foundations of modern machine learning. Okay, let's dive into this.
Just to make sure we tackle this whole thing logically, here's our roadmap. First, we'll look at the dawn of machine learning. Then, learning by example. After that, we'll break down the anatomy of data, hit the brute force barrier, and finally, we're going to conquer the problem by climbing the hill.
All right, let's jump straight into part one, the dawn of machine learning. We're specifically focusing on this massive, game-changing AI shift that hit in the 1970s and 80s.
So think about this scenario for a second. Imagine trying to describe your mother's face accurately using only words. Detailing the exact millimeter distance between her eyes or the precise curve of her nose, just so a complete stranger could pick her out of a crowded room. It's incredibly difficult, right? Almost impossible to get perfectly right. But if you simply hand that stranger a photograph of her, boom, they can recognize her instantly. And this brilliantly illustrates the core premise of our explainer today. In the early days of AI, engineers painstakingly tried to write out thousands of rigid, hand-coded if-then rules to teach machines. It was just so incredibly fragile. The visionary shift finally happened when researchers realized that machines, much like us humans, learn exponentially better from visual or data-driven examples than they do from strict engineered rules.
And that single realization completely transformed the landscape as we trace the history. Back in the 1970s, those rigid knowledge-based systems were really struggling to keep up. But then, in 1983, a bombshell publication called Machine Learning, the AI Approach dropped, and it triggered an absolute explosion of new research. It opened up entirely new horizons virtually overnight. By 1997, Tom Mitchell's legendary textbook systematized the field, taking it from this sort of niche experimental concept straight into the robust science we know today. So how exactly does a machine learn from an example? Well, let's transition to section 2, learning by example. We're going to introduce a really tangible case study to make all these abstract theories perfectly clear. Meet our central narrative, Johnny's pies. Now, Johnny is notoriously picky about his desserts. In our data, we've got 6 pies that he actually likes, and another 6 pies that he absolutely refuses to eat. Notice the visual differences between them all. Some are square, some are circular, some have thick crusts, others have really thin crusts, dark fillings, light fillings. It's quite a mix. Our goal is to train a computer to analyze these distinct examples and figure out exactly what makes a good pie, according to Johnny's highly specific tastes. In the machine learning world, this collection of examples has a very specific name. It's called a training set. It's simply a collection of pre-classified positive and negative examples. Think of it like the foundational textbook we're handing over to the computer. From this concrete set, an algorithm's entire job is to induce a reliable classifier, meaning it builds an internal mathematical rule that can accurately categorize literally any future pie Johnny might ever encounter. But, okay, here's the major hurdle. A computer doesn't have eyes, and it certainly doesn't have taste buds to sample these desserts. So ask yourself, how do we actually translate the visual, delicious concept of a pie into a language the computer can natively process? Well, that brings us right to section 3, the anatomy of data. The answer is data extraction, which we organize as a structured table. We essentially break the pie down into specific, measurable attributes. Just look at the columns we establish: shape, crust size, crust shade, filling size, filling shade, and finally, the class, whether it's positive or negative. Let's walk through that first example, x1, together. The machine notes its shape is a circle, it has a thick crust size, a gray crust shade, a thick filling size, and a dark filling shade. And finally, it logs that this specific combination sits securely in the positive class. So when the machine looks at that first pie, it absolutely does not see a warm, inviting picture. No way. It sees the exact conjunction of attributes. Shape equals circle, and crust size equals thick, and crust shade equals gray, and filling size equals thick, and filling shade equals dark. That string of logic, that completely sterile attribute vector, is exactly what a machine's data input looks like when it's analyzing a slice of pie. Which brings us to a really critical roadblock in section 4, the brute force barrier. You might be wondering, if we already know the attributes, why can't a computer just use its massive processing power to randomly combine these attributes and guess every single possible rule until it finds the perfect classifier? Now, what's really interesting about this is the math behind that assumption.
If we multiply all the possible attribute values together, so 3 shapes times 2 crust sizes times 3 crust shades times 2 filling sizes times 3 filling shades, we get 108 total possible distinct pie combinations.
But wait, the machine isn't just looking for one single pie, right? It has to find a specific subset of those pies that perfectly represents Johnny's unique preferences. The number of possible subsets is 2 to the power of 108. Just take a second to appreciate the massive scale of that problem. That is an astronomically large number, like far greater than the number of stars in the observable universe. Random guessing is completely mathematically impossible here.
As author Miroslav Kubat confirms in the source material, running each of these classifiers through the training set is clearly out of the question. Brute computing force is entirely useless here. We desperately need a smart, efficient search algorithm to navigate this massive space of possibilities.
Enter the hero of our story in Section 5, Climbing the Hill. Let's introduce the hill climbing search algorithm.
Think about how a search agent works. Any search problem involves an initial state, a set of search operators to make changes, and a final state that we want to reach. But the agent navigating this environment really needs a guide. Think of the evaluation function like a compass. Its whole job is to estimate the distance from our current state to our ultimate goal, which in our case is a perfect classifier with 0 errors. It essentially tells the algorithm whether it's getting warmer or colder with each step.
The hill climbing algorithm loops through a logical progression, step by step. Step 1, it starts at a random initial state, just an absolute guess. Step 2, it applies search operators, like adding a new rule, to generate a slightly different variation of that guess. Step 3, it evaluates the error rate of this new variation against our training set. And Step 4, just like a climber stepping upward on a mountain, it moves to the better state, the one with the consistently lower error rate. And then it just repeats the whole process. Let's actually watch it work on Johnny's pies. Our initial state guess is super simple. Let's just assume Johnny likes circular pies. We run that rule against our 12 training pies. It gets 4 of them wrong. So our starting error rate is 4 out of 12. Hey, not terrible, but we can definitely do better.
Let's move to and see how this builds. Next, our algorithm uses a search operator to add an AND condition. Now the rule is, Johnny likes ties that are circular and have a dark filling. Because we specialize the rule, making it way more specific, the error rate drops beautifully to 2 out of 12. We are officially climbing the hill. Finally, the algorithm uses another operator to add an OR condition, a disjunction. The machine's rule is now, Johnny likes pies that are circular with dark fillings, or pies that aren't circular but have a dark crust. We test this updated rule against our training set, and the error rate is exactly 0 out of 12. We have officially reached the summit. The machine has successfully created a 100% accurate classifier for Johnny's pies.
To wrap up this digital lesson concisely, here are the 4 core requirements for hill climbing to work. You absolutely must have an initial state to start from. You need a set of search operators to fundamentally change the rules. You need an evaluation function to tell you if you're getting warmer or colder. And finally, a termination criterion, like hitting 0 errors or simply reaching a hard time limit. Which brings us to a final, slightly provocative thought. If a computer algorithm can start with a totally blank slate, extract visual attributes into data, and learn to perfectly sort pies using a simple hill climbing search, what else in your world is it currently learning to classify? Think about facial recognition on your phone, the spam filters in your email, or the autonomous driving software in modern cars. The foundational logic is exactly the same as Johnny's pies. I really hope this explainer helped you grasp the fascinating roots of machine learning. Keep learning, and I'll catch you on the next explainer.